Okay, let's get started. Good afternoon, everyone. So in today's lecture, we are learning about a slightly different topic. We are talking about wireless and mobile networks. So in this chapter, we are going to learn some characteristics of both wireless and mobile networks, and we will see how wireless does not always imply mobility. And we are going to see some of the challenges posed by being wireless and being mobile as well. And we, of course, learn about how to address these challenges in today's networks. We are going to go with some concrete examples, mostly on Wi-Fi. It's also called EE 802.11 protocol. And a little bit about the cellular networks that we use every day, because it is the largest example of both wireless and mobile networks. That is the cellular networks we use, 4G, 5G, and so on. So before this, let's get started with some introduction about the cellular evolution. So it started with the first G, later what we call the 1G, and today we have 5G, right? And what that evolution means is we have a continuously evolving technology. And in the first G's case, it was all analog. And then in the 2G, the main improvement was converting it in all digital. And, well, what's the benefit of having digital? Well, all the signals we send over these networks was just analog signals. So these are like sinusoidal waves. This is how we encode information. But if you have an analog wave, let's say let's enable pen. Okay. So when you have an analog wave like that, and it gets transmitted, it gets distorted. There are many ways, many reasons it gets distorted, but let's currently assume that it gets distorted. So instead of receiving this, your receiver would receive something like maybe this. And in analog, there is no way to reconstruct it back to the original signal. Whereas in the digital's case, we first encode data into bits, into zeros and ones. And later we modulate that into a sinusoidal wave. But in between, let's say I have my symbol 0, 1, 1, 0, 1, 1, 1. How many bits? Let's add one more thing. So this is an 8-bit sequence, and I want to transmit this. Before modulating it into a sinusoidal wave, in digital communication, what I do is I do encoding. I can use error correction and detection codes. What that does is, this is an 8-bit sequence. It adds redundancy in a smart way. So now I have a sequence longer than that. This is just smartly encoded signal, let's say. And now this is maybe 16 bits. And even if my signal gets distorted and some of the bits are flipped when I receive them, I can still reconstruct it back to the original 8-bit sequence. Let's say this bit got flipped and it was received as 1. That's no problem. In digital communication, I can correctly receive it. Even if I do not receive it correctly, I can know that there is an error by using error detection codes. No, those are not our topics today. We're not dealing with channel coding or information theory in the first place. But this is one of the challenges posed by wireless communication. We have reasons for signals to get distorted, and we have methods to correct them back with the digital communication technology started, at least not started, but let's say widely commercialized with 2G. And now what came with 3G is, I think most of you remember that, was the video calls. Suddenly we can connect to internet with our phones. We can make video calls in real time. And that also enabled smartphones. And then what came with 4G is just an improved version of 3G. Now we have even higher data rates. We can play online games with lower delay. We can support 4K video, even 8K video in some cases. But what comes with 5G then is not just an improved version of 4G. We have 3 more pillars. That is enhanced mobile broadband, in short EMBB. This is just more bandwidth, higher data rates, and so on. This is the first pillar. The other one is ultra reliable low latency communication, or URL, reliable, no, that is URLLC. And what we also have is massive machine type communication. So instead of just supporting human users with 5G, we suddenly realize the need to support these machine users and all these low latency applications, some of which may be mobile or may require wireless connection. To give an example of that, let's think of a factory with a lot of moving components, so you cannot attach wires to each component, and these components need to communicate. Let's say in one production band, some machine is producing some metal sheets, and it gives it to the next one. The next one needs to acknowledge that it received it so that it can bend the metal and gives it to the next, and then the other one attaches to a car. So in all these factories with moving parts, autonomous components that operate together with certain communication requirements, now we can use 5G's massive machine type communication. So it can support so much more number of devices than would be required by just human-to-human communication. Well, humans are limited in numbers, obviously, and your mobile devices may be limited in numbers, but in a small factory, in a factory in a small region, there can be maybe hundreds of thousands of sensors and actuators all communicating. This support is provided by massive machine type communication. And for URLLC, you can think of perhaps very, very low delay and highly critical applications like self-driving vehicles communicating with roadside units or with each other, where every packet needs to be delivered in 1 or 2 milliseconds at most. Or you can think of certain remote surgery applications, remote control applications, the failure of which, or the jitter, network jitter of which would cause the death or injury of the patient and so on. So that is provided by URLLC of 5G. And EMBB, you can think of this an improved version of 4G's high data rates and bandwidth. Okay, so this is just the story of how useful mobile and wireless technologies can be, and why supporting them is important. And in fact, there is an existing use case that we use today, 4G and 5G. So when you use 5G, maybe you're not thinking it is that important. 4G was enough. Perhaps that's true for you, but again, if you think of all the applications they can support, the machine type communication and so on, they still have their own use cases. I think in the slides I uploaded, there's more detail on that, but I won't be going through here. So this is just some story on why we need wireless and mobility. Okay, so let's go back to here. Yeah, to give you more data, more motivation on why wireless and mobile is important. Well, even in 2019, we had more mobile phone subscribers than fixed phone subscribers. This is again just the motivation for the human user, but again, we have machine users. We have more mobile broadband connected devices than fixed broadband connected devices. Well, even here in your home, you perhaps have a mobile. In your home, you perhaps have a fixed broadband connection, that fiber optic connection coming to your home. But in a household of 3 or 4, you have a mobile subscription for every person. And another point is, well, the 5G's future will be more defined by software-defined networking, or SDN. So the idea in SDN is to decouple the infrastructure of wireless networks from this expensive proprietary hardware. So we can think of it this way. Previously, maybe 20, 25 years back, we had a different gaming device for different purposes. We had the Game Boy, we had Nintendo Game Boys, and we later had PlayStations. Even before that, we had an Atari, that device. You just insert the disc and you can play games on your television. And these devices were not interoperable. We have to develop games specifically for the target platform. And the users need to buy that platform's hardware to play that game. But today, we run almost all the games on computers. Not all, but almost all the games on computers. So you can think of computers as a generic hardware that can run any software, pretty much any software, at least gaming software. And all the hardware components are virtualized. So you can control everything with keyboard and mouse. And you get it displayed on your monitor. So a similar shift is going on with mobile and wireless networks, specifically the 5G networks. Now they are virtualizing most of the functions in software. So instead of having a firewall device that you put in your enterprise, now you're running it in software in your computer. You can even run a 5G base station on your computer. You can perform all the core network, access network functions. You can emulate it in your computer in software. Of course, you need to attach perhaps an RF front end, that radio antenna that your computer lacks. But in theory, you can just run that software in your computer and transmit and receive packets through that RF, the radio frequency front end. Yeah, so as I said, in doing all this, there are two important challenges, the wireless and mobility challenges, and these challenges are different. So wireless here means that we need to transmit information over wireless links, and wireless transmission is unreliable compared to wired transmission because the packets are now subject to noise, and they're also subject to fading effects. As you go farther from the source, the signal strength attenuates. So just like my voice being attenuated as it goes farther to you, while I'm speaking using microphone, but let's assume I'm not, it attenuates towards you. And there's also another effect. It gets blocked by objects, right? Someone outside won't be hearing me because there is a huge wall between us. And there is one more challenge. Well, we have to design things for multiple access. Well, if all of you talk at the same time, we will have collisions. And in the mobility challenge is different. Well, you have to think about how to address every user if they are moving around. So now you're all here, I can talk to you, but if you move somewhere, how do I address you? I need to find your new information, new location information. So what happens if you change point of attachment to the network? And so that's also a challenge. And in this chapter, we are going to learn about how to address these challenges specifically. So this is kind of a promise of empowerment, what you will learn at the end of this chapter that you don't know now. So first, we are doing wireless. We are going to look at some of the wireless links and network characteristics, some terminology first. We're going to learn about what a base station is, what a wireless host is, and so on. Then we're going to look at Wi-Fi as a use case, how it handles the wireless challenges. Then we are going to mobility. We're going to see some of the principles of mobility management, the mobile IP protocol, how it is being handled in today's internet, and how it is being handled in mobile networks. We're briefly looking at that as well. Okay, any challenges before we start? Sorry, any questions before we start? All right. So let's start with some terminology then. So in a wireless network, well, we have what we call these clients or hosts of before, all wireless hosts. So this PC is a wireless host. Maybe I use a different color here. So these are all wireless hosts, be it your cell phone, be it your mobile phone, be it your computer device, be it your fridge in home, or your robot that cleans your floors. All of them can be called wireless hosts. And obviously these hosts run applications, right? We run applications for them to operate. And the sole reason we want to support them over wireless is that they run applications. And some of them can be stationary and some of them can be mobile. So wireless does not imply mobility. For instance, your fridge, I don't think you move your fridge every day from the kitchen to the bedroom. It stays in the kitchen. Or when you just study on your laptop over at Starbucks in Newtown, if you stay there, you are in fact stationary from the perspective of the network. You're still attached to the same point, same access point. So yeah, again, wireless does not always mean mobility. So this is our first point. Next, we have the base station. Well, in this context, we refer to all the access points as base stations, not just cellular access points. So in this case, your Wi-Fi router would be a base station, just like a cellular base station at a cell tower would be called a base station. So this is our terminology here. And typically, the function of these base stations is to relay packets to and from these wireless hosts. So there is a network elsewhere, maybe the internet, and these base stations are connected to the larger internet, typically via a wired backbone. So they have these very high data rate cables coming to them, and they relay every incoming and outgoing packet to and from the hosts, the wireless hosts. So they perform what we call relay function. And examples of that is, again, cell towers, and this is Wi-Fi access points. So your Wi-Fi router at home would be called a base station. And what we call these links between these base stations and all these wireless hosts is wireless links. As the name implies, they are used to link mobile devices or wireless hosts to the base stations. Sometimes, not always, these backbone links that you see from base station to the wired network infrastructure could also be wireless. So it is possible that they have a very high rate wireless link to relay your packets to and from the larger network, larger internet. But typically it is wired, because in wired we do not have the challenges posed by all the mobility and wireless stuff. And let's go back to our discussion on these wireless links between the wireless hosts and the base stations. Well, typically we use certain multiple access control protocols to coordinate the link access. So if all of us talk at the same time, we won't be hearing anything. So we do not want all the wireless hosts to talk at the same time, because they would interfere with each other, right? And we use certain multiple access protocols to regulate exactly that. we're going to look at that over an example of Wi-Fi. Well, depending on the protocol, depending on the use case, we can have various transmission rates, distances, frequency bands, all kinds of different implementation options for these wireless links. To give you some examples, I think this is not a great figure, but yeah, just to give an idea of how different it can be. So 802.11 again is Wi-Fi, and we have different versions of Wi-Fi. So on the y-axis, you see the data rate that can be supported by the protocol. These are also kind of Wi-Fi. And Bluetooth is not too different than Wi-Fi. It's using pretty much the same antenna, same RF front end. But depending on the use case and depending on the evolution, over the evolution, we have higher data rates. We have different data rates, and we have different use cases. Some Wi-Fi protocols or Bluetooth can only be used in indoors because they do not propagate as long. Some of them can be used up to maybe 50 meters or so. Well, for 5G, I think this is not accurate to place 5G here because, as I said, it can support so many use cases. We have 5G applications that can perhaps support, yes, 10 gigs per second, but we also have 5G applications, such as those for massive number of machine-type communication devices that do not need to support those high rates. Maybe they support a few megabits per second, but they can propagate very long distances, and they can support access by so many users. They can coordinate so many users to communicate with the same base station, same access point. So 5G is pretty diverse in that sense. I'll also discuss about two operating modes. Again, we are continuing on the terminology here. Infrastructure mode and the ad hoc mode. Well, infrastructure mode is what we already discussed. We have base stations coordinating all the devices around them and relaying packets to and from them, between them and the wired network infrastructure. So, in other words, the base station here connects mobiles into the wired network. And in the infrastructure mode, let's say some wireless host is changing its location, in particular this guy here. It is moving from the base station on the left to the base station on the right. Well, in that case, we have to handle mobility, right? Let's say you are at this host sending data over to this guy. Well, how does it go? Well, you have to send it through your base station here. Then it goes to the wired network infrastructure. But then wired network infrastructure needs to know whether it should route this packet through here or here. So we need a handover algorithm, handover procedure between these two base stations coordinated by this mobile host. We are going to look at that in this chapter. So that was infrastructure mode. We relay packets to and from the wireless hosts using base stations. But we also have this ad hoc mode. And in this, we do not have base stations in between. And all the wireless hosts self-organize themselves into sending packets to each other, communicating with each other. So here, no base stations, and they can, because of that, they can only transmit to other nodes within their link coverage. So here in this example, you can see with the disks around each mobile host, the communication range of each of them. Obviously, it would not be an exact disk in the real life, in the real scenario, but this is just an approximation. But if they are, the point is that if they are too far, for instance, this mobile host, this wireless host is too far from the others, so it is not in the range of the others, and it cannot communicate with others. So that is an issue. But this guy is also not in the range of this guy, but if these wireless hosts coordinate themselves, they can potentially relay the packets between each other. And there is a lot of research, a lot of techniques about how to organize these kinds of mesh networks to provide the functions, at least most of the functions provided by the infrastructure mode. And why would you have this mesh network if you can build the infrastructure? Well, you probably don't. Having infrastructure is better, but there can be certain applications where it is not feasible to have an infrastructure. For instance, let's say you are running drones over desert. There is no cell tower, there is nothing in there, so you need your drones to communicate with each other and organize that way. Or maybe you're doing space exploration and your satellites can only communicate with each other because obviously we have no base stations over there. Or, even in a factory in a remote location, maybe if you do not have any wireless service, or in a ship, if you do not have any mobile network nearby, or you're not using satellite communications, you can use ad hoc mode to coordinate between the ships and so on. Any questions? Okay, yeah, so that was just some terminology. Yeah, to repeat very quickly, we had wireless hosts. These are all these devices that connect to the internet, not necessarily internet, that connect to the network. We have base stations that are typically connected to the wired network, and they are responsible for relaying data to and from these wireless hosts. And what we call between these wireless hosts and the base stations are wireless links. And we also learned about two modes: infrastructure mode, where we have base stations coordinating wireless hosts, and the ad hoc mode, where we don't have base stations, but the wireless hosts organize themselves. Okay, so that was some intro and some terminology on wireless. Now we are looking at wireless links, some of the challenges posed by the wireless environment, and then how to address that. So first of all, in wireless networks, we have decreased signal power. This is also called path loss. And well, why that happens? Because any electromagnetic wave, as it propagates, its strength reduces. If you project light somewhere, as you get farther from the source, you get less light per area. Or even in sound waves, when the destination is farther from me, the destination will be hearing me less. So that is decreased signal strength from path loss. And there can be other ways why we experience path loss. That is called shadowing. What is shadow? If you're blocking the source, you have a shadow behind you, right? Same thing here. Anyone outside won't be hearing me well because this wall shadows my sound waves. And next we have interference from other sources. Again, if all the sources are transmitting on the same frequency band and at the same time, it's like talking all at the same time. So we would have interference and our packets may collide. Anyone listening to either one of the transmitters won't be hearing the transmissions well. So this is what we call interference. Let's also add shadowing here. And we also have multipath propagation. Well, this happens when radio signal reflects off the objects. So to give an example of that, well, think about the light sources here. There is a direct light coming to your eyes, but it also reflects from surfaces. It diffracts and reflects from the surfaces, and it scatters from the corners. So we see, in addition to the main light source, we also see all these reflections around, and that is also how we see these objects around us. So this is multipath propagation. We have, instead of having one direct line of sight signal, we have all these paths, all these multiple paths added on to each other. But the problem in this case is not just, adding them all additively, but let's say this is my source and this is my destination. There is direct line of sight signal, LOS. Let's say this is my ground, and there is also another component of that signal that is reflected off the ground and arrives at the destination. Well, obviously the red signal here propagated less distance than the blue signal. So if you're sending a sinusoidal wave, let's say, your first component, your blue component, will arrive slightly late. What happens when you add these two signals? You no longer have a sinusoidal wave. You have something distorted. This is multipath. And we have a lot of methods to prevent this, or at least to mitigate the effects of this, one of which is using, of course, error detection and correction codes. But we also have other methods like using multiple antennas, beamforming techniques, and so on. But those are not, our within our scope. We are only discussing these to understand why wireless is challenging. So overall, all these things together make communication across wireless links much more difficult. Yeah. Oh. Okay, I think what we also don't have here is obviously noise. Let's also add something like this. Yeah. You might also have noise in the wired communication if your cables are not isolated, but typically all these cables are covered with certain material with the correct electromagnetic properties, so they isolate outside noise. But around us, there is always thermal noise. And this noise affects the signal received. So always what we receive at the destination is some main signal component after being distorted from all these multipath effects, shadowing and path loss and so on, and some noise component. And where does this noise come from? Well, it comes from thermal noise around. Every object, just because of just for having certain thermal energy, they emit electromagnetic radiation. And this is also how we see sun. The sun makes what we also call blackbody radiation. Because it is too hot, we can see that easily. But even without sun, the objects around us, even this table here, or you are emitting a little bit of electromagnetic radiation because your temperature is above 0 Kelvin, which is minus 273 degrees Celsius or something like that. And because of this radiation there is a very small amount of radiation, but all the objects are emitting that. And because of all these small additive effects, we have the noise. So no matter where you're listening over the Earth, you will have a lot of noise coming from the Earth itself, the objects around. Even if you're not interfering with the signal, you will still have the noise. And we typically model this noise using Gaussian distribution because it is a very unpredictable component. Very small pieces of matter is making black body radiation in an unpredictable way. And because of the central limit theorem, when you have so many independent random variables added, independent identically distributed random variables added to each other, you converge to Gaussian distribution. So it is typically modeled using Gaussian distribution. But again, what is important for us here is that the noise also distorts the received signal, and it is another challenge posed mainly by wireless propagation. All right, now, any questions on the challenges of wireless propagation? All right, good. So we also have another challenge caused by interference. In this scenario here, on the left, we have three nodes. We have A trying to communicate with B, and we also have C trying to communicate with B. Well, typically, just like what humans do, when we are in a room, in order not to speak at the same time, we usually wait for each other's speech and then start communicating and then start talking. For instance, now that I'm talking, none of you is talking. But if I was not talking and I leave the room, I think some of you will talk to each other. So we do not speak at the same time because we listen to each other, and if no one else is speaking, then we speak. Well, the wireless multiple access protocols are structured in a similar way. Well, A here will listen around. If A does not hear anything, A will start transmitting to B. Same. C, if C wants to communicate with B, C will listen around. It will sense the spectrum. And then if it doesn't hear anything, it will start transmitting to B. But in this case, there is an object in between A and C. But that object does not prevent them from communicating with B. So what happens is A and C cannot hear each other, but they are both sending to B. And because B is receiving two signals at the same time on the same frequency band, these transmissions will interfere with each other. So if you look at the signal strengths here, A signal is strong near A. It is still strong. It experienced path loss a little bit, but it is still strong at B site, but it gets very low at C site. So C won't be hearing that. Same thing here. For C signal is strong here. It is still strong when it comes to B, but when it arrives at A, it experienced shadowing because there's an object in between, right? So in this case, A and C will not notice each other. In other words, they will be hidden to each other. This is also called, therefore, the hidden terminal problem. Both terminals are hidden to each other. So how to address this challenge? It is not that easy. So sensing as a method of preventing collisions may not be enough. So I'm going to show one example of addressing that. This is called code division multiple access, or CDMA. So previously I think you have learned the ways of achieving multiple access. Well, one is using frequency. Oops. Let's say, oh, what's going on? Ah, that's funny. Anyway, I'll try to write on another slide. Okay. Okay, let's say this is time and this is frequency. And we have A and B transmitting. Well, one thing you can do is you can assign each of them to transmit at different times. You have A transmitting here, you have B transmitting here, and then you have A transmitting here again. You can do this for more than 2 transmitters as well. This is time division multiple access, TDMA. You've learned this in the first part of the class, am I right? Okay, good. And in FDMA, frequency division multiple access, we have it the other way around. We have in the frequency, they are all transmitting in different frequencies. Okay, so for some reason I cannot write below the slides. That's interesting. But anyway, I think you got the idea. You have different nodes transmitting in different frequencies, like so. And now I'm telling you there is another way, which is code division multiple access, in which they can transmit using the same time frequency band, but their signals can still be decoded. And how do we do this? Well, we assign a unique code to each user. So here we are achieving orthogonality not in the time domain, not in the frequency domain, but we are achieving it in using codes, orthogonal codes. And all users share the same frequency, but they have an orthogonal code that they use to encode their data, the symbols, the bits for transmitting. And it allows multiple users to coexist and transmit simultaneously on the same frequency band with no interference in theory. And how we do it is we have the original data, the sequence of bits that we are sending, zeros and ones, and we get the inner product of that with the chipping sequence. And because we are in the Euclidean domain, this can also be interpreted as a dot product. And decoding is the same. We receive the sequence of bits at the receiver side, and we are again multiplying it. We are again getting a dot product of it with the same chipping sequence. And then we will be getting the original data. Now we will see that in action. So in this example here, we have a sender and the receiver. And the sender wants to send the bits 0, 1. Just 2 bits symbol. Well, these are the data bits here, D1 and D0. These. And, we are encoding zeros as -1s. So instead of writing zeros here, we are writing them -1s. And at the end, when we decode everything, the receiver will again decode that -1 into 0. So it makes no difference. Okay? So we have -1 and 1 here. And this code here is the chipping sequence for the sender. This is an arbitrary chipping sequence, or the code, assigned to this particular sender. For other senders, it will be another orthogonal sequence. And our sequence is 1, 1, 1, -1, 1, -1, -1, -1. So we are multiplying every symbol with this sequence. And after that dot product, this is what we have. Well, how did we calculate that? Well, I multiplied 1 with -1, it is -1, so I write it here. I multiplied this one with -1, again it is -1, so I write it here, and so on. Is that clear? And again, for the second symbol, because the symbol is 1, I'm multiplying 1 with 1. It is 1, so I'm writing here. I'm multiplying 1 with 1. I'm writing it here. 1 with 1. I'm writing it here. 1 with -1. I'm writing it here. So I'm just taking the dot product of these two vectors, in other words, this di and cm. And then, so this channel output is sent to the receiver, and if it is received correctly, it will be received as the same sequence, and then the receiver again multiplies that with the same code and performs this computation. Well, how it does it is very simple. Again, I'm multiplying these two, that is -1, multiplying these two, -1, multiplying these two, -1, multiplying these two, that is also -1, these two, -1, -1, -1, -1. And I'm dividing it with the length of the chipping sequence, which is 8. So what I have is -1, and this is what we have here. I can do the same for the second part, I can multiply all these things, and that gives me 1 plus 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 1 over 8. So this is my D0. And this was my D1. Okay? But obviously, this is the ideal communication scenario. We had one sender, one receiver. And you might be asking, well, what's the benefit here? I could have just sent these symbols as they are, and the receiver would be receiving them as they are, if you're assuming no noise, no channel errors, or something like that. Well, you're right. But the practical communication scenario is far from ideal like this. And CDMA works also in the presence of interferers. So even if we have an interferer here, another sender using another unique code, an orthogonal unique code, this destination would still be able to decode both transmissions using the chipping sequence. Now let's see that over that example. So I have here two senders, and well, the sender 1 is trying to send 0, 1, and the sender 2 wants to send 1, 1. This is the symbol. This is the data they want to send. And again, they are first encoding them as, they are encoding the zeros as -1s, so that's why I have a -1 here. And 1 is encoded as 1. And we are assigning different chipping sequence for both of them. Well, for the first sender, my chipping sequence is 1, 1, 1, -1, 1, -1, -1, -1. So that is this code here. And for the second one, I have a different orthogonal code. Well, I'm doing the same dot product computation. So if I do that here, for the first one, that would give me -1, -1. Now each of them are different bits, so I'm separating them. -1, 1, -1, 1, 1, 1. And for the second one, let's multiply this data bits with the second one's code. I have 1, -1, 1, 1, 1, then minus 1, 1, 1. Is that right? Okay. And then, obviously, because they are in the same vicinity, they are both sending that data to the same receiver, these transmissions get added onto each other. And in the channel I have, so if I add these two up, this is what I have. I have 0, I have minus 2, I have 0 again, I have 2, I have 0, I have 0, I have 2, I have 2. This is exactly what you have here. Well, you can do the same for the second symbol, but I'll skip it here. Any questions on this? Okay. Okay, now let's assume I did the same for the second symbol, and this is what the receiver received, because, you know, both of them are added together. And to resolve individual transmissions, then this is what the receiver does. Let's say it wants to resolve the first sender's, this one's transmission. It needs to multiply what it received with the chipping sequence of the first sender. So if I multiply these two, I have 0 plus minus 2 plus 0. So that comes here. Again, plus minus 2. Plus 0, plus 0, plus minus 2, plus minus 2. Yeah. Over, obviously, the length of the chipping sequence, and what I have is minus 1, which is what I have here. So even in the presence of an interfering signal, the receiver was able to decode the original sequence sent by the first sender using CDMA. Now that can be useful, right? Imagine you can have more senders, and you can decode each of their individual transmissions by assigning each of them a chipping sequence and using that chipping sequence when decoding. So now my question to you is, can I have infinitely many senders here? How many senders, up to how many senders can I have here? Any guesses? So in this example, I had two senders. They had different sequences. But both their transmissions were resolved at the destination. Up to how many senders I can have for their transmissions to be resolved at the receiver? Any guess? 2 to the power of 16. Why 16? But my chipping sequence here is only 8 bits. So it is only this. The second one is the repetition for the second symbol. To the power of 8? Okay, yeah, that is the number of different sequences you can assign to each user, right? But that's not correct. But that's a good guess. So the right answer here is as many transmitters as the length of your chipping sequence. Again, why is that? Because you want your chipping sequences to be orthogonal. And if you have a vector space of length 8, you can only have 8 orthogonal vectors. An intuitive explanation would be this. So let's assume we have chipping sequences of length 2. Okay, so we have a two-dimensional vector space. If this is the data symbol I want to send, well, the first sender projects it into one sequence and sends this symbol. And for sending the same, the second sender needs to project it into an orthogonal plane and send this. Now, whatever the first guy sends, it will only be in this direction, so it will not interfere with the other guy's transmission. And whatever the second sender sends, it will only be in this direction because, it projects whatever symbol it is sending into that direction, into that vector space. It will not interfere with the first guys because they are orthogonal here. Now, obviously, I cannot draw this same thing in 8 dimensions, but I think you can get the idea over this projection example. So in a way, in CDMA, we are projecting the symbols into a vector space. Any questions? Okay, then another question to you is then, let's say I have another sender here, sender 3. And this sender 3 has a chipping sequence of 1, 1, 1, 1, 1, 1, 1, 1, all ones. And if all these 3 senders communicate with the same receiver at the same time, in the same frequency band, would their signals be resolved or not? How do you check for orthogonality? Well, you just get the dot product, and if the dot product is equal to 0, then that means they're orthogonal. So I have 2 vectors, x and y. You get the dot product. If this is 0, then x and y are and that's really interesting. Whatever I write is deleted immediately. Okay, I'm trying to write orthogonal here. Okay, so if their dot product is 0, x and y are orthogonal. So in this case, you would multiply these, and what you get in the end is 0. You have to do this with both senders. That means sender 3's chipping sequence is orthogonal with both sender 1's and sender 2's chipping sequences. So you can use these chipping symbols, chipping sequences to communicate with the same receiver. If it doesn't end up 0, then you have a problem. You cannot use that chipping sequence. And I'm telling you that you can only find 8 unique chipping sequences if your code length is 8. That would give you that would give you orthogonal chipping sequences. Okay, any questions? Okay. Now that was some background about wireless links, wireless network characteristics, and the difficulties of wireless transmission, right? Now we see that over a concrete example, specifically the Wi-Fi's example, on how we address some of these challenges. But again, some terminology first. But more like the architecture. So in Wi-Fi, or EE 802.11, again, we have internet, and we have some switch or router of the internet, and we have an access point, or what we also call the base station in this wireless context. And this base station is in infrastructure mode. Remember, infrastructure mode was base stations relaying data to and from these wireless hosts. We have it in infrastructure mode, connecting wireless hosts to each other and connecting wireless hosts to the internet. Again, our access point is also called base station. Well, we can also have ad hoc mode. Well, you can also configure your computer to connect with another computer using its own Wi-Fi antenna, and that would be ad hoc mode without backbone to the larger internet, without a connection to the larger internet. So here in this example, we have two basic service sets, also called cells, because we have two Wi-Fi access points serving two cells. In Wi-Fi, we have two modes of scanning. Okay. So the problem here is, the question would be here is that, let's say you're bringing your laptop somewhere, and how do you connect to, how do you know there is a Wi-Fi network? Well, obviously what you do in practice is to check networks nearby, right? But how does your computer know these networks nearby? Well, there are two methods to do that in Wi-Fi. We can have passive scanning, in which the routers advertise themselves, their IDs, their security requirements, and so on. So your computer learns about that and then displays it in the user interface to you. But some access points can be in hidden mode. In that case, that would require active scanning. So your computer needs to send a probe request to receive the response from the nearby basic service sets or the access points to learn about their requirements and their IDs and so on. So in the passive scanning mode, the access point first sends the beacon frames to the wireless hosts, and let's say both of them are sending in this case, because our device is in the coverage area for both basic service sets. And then our device would be sending the request frame to the selected access point. So this is after you selected from your wireless host, your laptop, which access point you want to connect to. And to that access point, you send the association request, and then you also receive association response. If that is successful, you get connected. In the active scanning, on the other hand, this time you first request the probe request. You first send the probe request, because these base stations are not advertising themselves. They are not broadcasting their information around. You have to request that, and then you will receive the probe response in item 2, and then you will send association request, and then you'll receive association response. The rest is the same. So the only difference here is that you only send the probe request in active scanning first, and the base stations are not sending beacon frames. Okay, now let's discuss about how we address these collisions in Wi-Fi. Well, obviously, TDMA and FDMA are used to a certain degree here. Obviously, we have more than one channel, more than one frequency band, so multiple users can simultaneously communicate using Wi-Fi, using different bands, or they can also stagger their communication. They can transmit at different times, obviously. But what happens if more than two nodes transmit at the same time on the same frequency band? So now we are thinking about a single resource block, single time frequency block, and how to address that challenge, how to prevent them from transmitting to the same receiver who would be hearing both transmissions. So, in short, our problem is prevent more than 2 nodes transmitting at the same time. In other words, we want to avoid collisions. In CSMA, in carrier sense, multiple access, you have sensing before transmission. So you first hear, and then if you do not hear anything, you first listen. If you do not hear anything, then you transmit. And the purpose of that is not to collide with an ongoing transmission, right? But, so I think in Ethernet you also learned some form of CSMA, carrier sense. But you had, I think you learned CSMA CD, correct? Collision detection. Am I right? Good. So in Ethernet, what you do is, while you are transmitting, you also listen. But in Wi-Fi, while you are transmitting, you cannot listen. Because it is almost like trying to listen to a whisper when you are shouting. In wireless, attenuation is very large. So while I am sending, my own signal is very strong here, but some other transmitter signal is very weak here. So I cannot hear their transmissions, so I cannot perform collision detection, unlike in Ethernet, where the transmitted signal and the received signal are pretty much at the same strength because they are going through wires. There is almost no attenuation. There is no multipath effects. There is no shadowing and so on. Here I cannot detect collisions. But I can still do collision, what I call collision avoidance. So now, this was Ethernet. And this is Wi-Fi. CSMA CA. And CSMA CA is you are sensing before you are transmitting. When you are still silent, you can sense other transmissions. So it's similar to how we sense others talking, and we don't talk while somebody else is talking. But once your transmission begins in Wi-Fi, there is no way you can detect you can sense others' transmissions, because your transmission would be so strong that it would block others. Yeah, okay. I think we have learned about this hidden terminal problem here, right? This would still cause us problems because here A would not hear C's transmission. So A can start transmitting while C is transmitting. So we still need to discuss how to address that hidden terminal problem. But the main point here was that we have collision avoidance, not collision detection, because we cannot detect collisions in wireless. Now let's look at the CSMA CA protocol and how it works differently than CSMA CD. So this is, here we have the sender and here we have the receiver. So the first thing sender does is what? Obviously it needs to sense. It sends the channel for a while. Well, this name is not that important. It just senses the channel for a while for what we call the distributed interframe space, or DIFS. Well, if there is no transmission, then it starts transmitting data to the receiver. And then the receiver, if the frame is received fine. After waiting this SIFS, short interframe space, whatever, it sends the acknowledgement. Why do we have acknowledgement? Well, again, wireless transmission is quite unreliable, so we want to acknowledge every data, every packet that is received. And if we do not receive acknowledgement, well, the same process needs to be repeated again. But now let's assume that in this DIFS interval, the sender sends the channel to be busy. It's not idle, so it cannot send data. What does it do? It starts a random backoff time. In other words, it waits. So it generates a random variable, a pseudo-random variable, let's say 16 milliseconds, and it waits for 16 milliseconds. And after that timer ends, it transmits. Again, if there is acknowledgement, that's fine. If there is no acknowledgement, we then increase the backoff time. Now, I do not wait 16 milliseconds, but I wait more. Well, not necessarily more, but let me say this. So first, it throws a random variable. Let's say it throws a exponential random variable with a mean of 8, and then it throws a random variable with a mean of 16, and next time it throws a random variable with a mean of 32. So on average, it increases the waiting times every single time a failure occurs. If every single time the acknowledgement does not arrive, it increases the backoff time probabilistically, not for sure. Yeah. Okay. So there's one other difference with the CSMA-CD protocol here. So in CSMA-CD, the station begins transmitting as soon as the channel is sensed idle, right? But here, we are sensing the channel busy, and when it is idle, we are still starting the backoff, the exponential random backoff. So we're not immediately transmitting when the channel is idle. It becomes available, and then we start backoff. Why do you think we need to have a random backoff time here, unlike Ethernet's CSMA-CD? Yeah, so to repeat the question, let's say this is our timeline. Now, we are sensing the channel busy, right? In CSMA, whenever that busy period ends, what's going on? This is CSMA-CD. Whenever that ends, we can immediately send. Whereas in CSMA-CA, case of Wi-Fi, we have some random backoff period. And even if the channel is idle during that period, we still count down until that backoff timer expires, and then we send. CSMA-CA, collision avoidance. Why do you think is the difference? There is a deliberate reason for that. Yeah, I would like to just get some guesses here. I think this is also key to understanding the difference between collision detection and collision avoidance. So you can think in those lines. Here, if we do not have collision detection but collision avoidance, what difference does it make in having immediate transmission and waiting for a random backoff? Any guess? Well, okay, the answer is, well, in CSMA-CD, because we have collision detection, even if somebody else starts transmitting right here, we can still stop our transmission. But imagine this scenario. The channel is busy, and all of us, let's say there are 10 transmitters, and each of them is waiting for that transmission to end. And whenever that transmission ends, we all send at the same time, because we were waiting to be talking, right? Well, in CSMA-CD, that's not a huge issue, because when you all start talking at the same time, you can detect the other 9 transmitters talking, so you can stop. Whereas in CSMA-CA, you cannot detect others talking when you're talking. So if all those 10 transmitters start transmitting all at the same time, well, they'll keep talking until their frames end, and that's a long time. In wireless, these frames can be larger, and until that ends and you receive no acknowledgement, then you realize and you send everything from start. Whereas in CSMA-CD, the collisions are not that costly, so you can start immediately transmitting without waiting random backoff. Is that clear? Okay. Yeah, okay, so I talked about the hidden terminal problem, right? A and C cannot see each other, they cannot detect each other. So this collision avoidance cannot prevent that hidden terminal problem, because A and C won't be hearing each other in the first place. They won't avoid each other's collisions. Now there is a method to avoid collisions for hidden terminals, and in that the sender reserves the channel using the feedback from the receiver. Here in this RTS-CTS sequence, request to send and clear to send sequence, this is a very simple reservation mechanism. The sender sends a small request to send packet to the base station. Well, you might then ask, well then if all transmitters start sending these RTSs at the same time, then again, why they don't collide? Well, they do collide, but these RTSs are very small reservation packets. They're not data. They're not 1 kilobyte or something. They're just very small. You know, I want to reserve this channel, and my ID is this. Well, even if the RTSs collide, they can easily send RTS again. And then the base station broadcasts, or the receiver in this case, broadcasts the clear to send in response to the RTS. So let's say 10 of us are all waiting in line. We all send RTSs, again, after random backoffs. And probably one of our RTSs will arrive first because we draw random variables, right? They are very unlikely to be the same random variable or very close random variables. And whenever the first RTS arrives, the base station or the receiver will then reserve that channel to that transmitter using clear to send packet. Both RTS and clear to send, both RTS and CTS are very small, but they are short. So even if they collide, that's not a big issue. And this clear to send is heard by everyone around. So the 9 others around will be hearing clear to send destined for someone else, so they will keep delaying their transmissions. Now let's see that over this diagram as an example. So we have hosts A and B, and they are hidden terminals, meaning that they cannot hear each other, but both of their transmissions can be heard by the access point. So they both send reservations. Well, by some small chance, their reservations may collide at the access point. Well, if that collides, well, they will just send again after a while later using random backoff. And let's say in this case, the wireless host A's RTS arrived first. So this access point received RTS from A, and because it received RTS from A first, it will reserve that resource for A. So it will broadcast to CTS. So the key point here is that it is sending CTS not only to A, but to everyone around, so that everyone who can hear the access point will be hearing that the resource block is, the time frequency block is reserved for A. And because this is reserved for A, B will defer transmissions, and A can send its data. If all goes fine, it will receive an acknowledgement, and then B can send an RTS. All right, any questions here on any parts of the lecture today? Okay. So I think I won't go through mobility today. But in the next lecture, we are going to first start with the difference between wireless and mobility. Then we're going to look at ways of supporting mobility in wireless networks. So I uploaded your first tutorial. Again, I think I'm going to solve it on next Wednesday or next Friday at worst. So please attempt the first 2 questions. You can ignore the last question, which is on mobility. I'll do that after we finish mobility. And I plan to upload the CA2 this weekend, so you can have a look. I'll give you around 4 weeks to complete it. All right? Yeah, thanks all, and see you next week.